Section 1.7 talks about diagonal, triangular, and symmetric matrices. A square matrix, again, recall square means the number of columns equal the number of rows, so n by n. A square matrix in which all entries of the main diagonal. Now, the diagonal is this. All entries of the main diagonals are 0 is called the diagonal matrix. So if you look at D right there, if you have 0 everywhere else other than the diagonal, we call that the diagonal matrix. And this this matrix has a very special properties. And we're gonna later on in the course, we're gonna take a matrix A and write it as a product of 3 matrices. One of them is the diagonal matrix because it has certain properties. If you have a diagonal matrix, if you want to find the inverse, it's simply 1 over the diagonal entries, whatever those are. If you take a diagonal matrix and raise it to a power, you simply raise each diagonal entry to that power. This is not true for any other matrix. If you take A and you square it, you have to multiply by itself. If I take A and I raise it to the 10th power, the only way to find that, if I'm not going to do what I said, find the diagonal matrix, is to multiply by itself 10 times. And that takes a while. Now, if you have a diagonal matrix multiplying a matrix on the left, so on the left, meaning if the diagonal matrix right there is on the left of a matrix A, you really end up multiplying D1 times the first row, D2 times the second row, and it runs in order, and D3 times the third row. And as you see, D1 is right there, multiplied by all of these terms, D2 is right there, and D3 is right there. So, if you're multiplying a matrix on the left by a diagonal matrix, you end up just multiplying the rows accordingly. Row 1, row 2, row 3. If you multiply a matrix A on the right by D is a diagonal matrix, assuming it is, then you end up multiplying the columns as you see. It's right there. So this is a very unique property. Now, of course, we're going to practice that and show that, that's how it is. But if you could do that, then that saves you a lot of work. And a diagonal matrix is a matrix, again, in which the diagonals are all, let me use my laser pointer, the diagonals are all the only numbers that could not be 0. Everything else is a 0. All right. Now, triangular matrix. So a square matrix, again, that's an m by n. So 2 by 2, 3 by 3, 4 by 4. A square matrix in which all the entries above the main diagonal, and again, the diagonal is right there. If all the entries above the main diagonal are 0, we're talking about this one first, then we call that lower triangular because all the values are on the bottom of it. And a square matrix in which all the entries below the diagonal are all zeros, we call that upper diagonal because all the numbers are there. A matrix that is either upper diagonal or lower triangular is called a triangular matrix. Now, what's so important about that is that if you have a lower triangular or an upper triangular, let's say we're looking at this right here. Well, here I could read that A11 equal, if this is an augmented matrix, I could figure out exactly what that is, substitute it down here to figure out A sub 2, 2, substitute both of those to figure out A sub 3, 3, and the list goes on. And if you're dealing with the traditional triangular matrix that we've been playing with all along, so if you have an upper triangular, we know that we could figure out, say, in this case, x4. Once we figure that out, you plug it in and figure out x3 and so on and so forth. So a triangular matrix is very important to solve an augmented matrix. A square matrix is said to be symmetric if you take the transpose of it. Remember, transpose is when you switch the rows with the columns, and it turns out to be the same. So here we're dealing with few classifications. Classify the matrix as, is it upper triangular, lower triangular, diagonal? Decide by inspection whether the matrix is invertible. Recall that a diagonal matrix is both upper and lower. Now, I do want to talk about invertible. It seems I skipped that theorem. Okay, I found it. It seems I forgot to get this one. Well, out of those, I'm really more interested in C than any of the other things this term says. It states that transpose of a lower triangular matrix is upper triangular, and the transpose of an upper triangular is a lower triangular. The product of a lower triangular is a lower triangular, and the product of an upper is an upper. Here, this turns out to be crucial for what we need. It says a triangular matrix is invertible if and only if its diagonal entries are all non-zero. If one of the entries are zero, then this is not invertible. And the inverse of an invertible lower triangular matrix is a lower triangular, and upper is upper. So again, C is really what I was after, and that's why they were saying here, decide by inspection whether the matrix is invertible. So I'm looking at number 2. Number 2, since the zeros are up there, we say that's lower triangular. And it is invertible since none of the entries across the diagonal is 0. Here we have upper triangular, and we say this is not invertible because one of the entries is 0. And if I get to the next problem and I proceed, so there's a lot of classifications in this section. Here we would say this is a diagonal matrix, which means it's an upper triangular and a lower triangular. And since none of the entries across the diagonal, again, this is the diagonal, are 0, we say this is invertible. And on the last one, well, obviously that is a lower triangular, and it is not invertible since we have a 0 on the diagonal. Now, remember, multiplying on the left, you multiply the rows. Multiply on the right, you multiply the columns. Okay, so recall that. Let's practice that a bit. If I look at this, I notice that this is a diagonal matrix. You're multiplying on the right. If you're multiplying on the right, then that's going to be really 1, negative 3, 2, negative 1, negative 5, 0. And what you're going to do, you're going to multiply the first column, the second column. So we're going to multiply by a negative for each of those. Oh boy, the level of this, that. And we're going to multiply by a 3, and we're going to multiply by a 2. And the outcome of this will turn out to be a negative 4, 6, negative 10, a 12, negative 3, and a 0. And if I look at the next problem, so again, I notice there's a diagonal there, a diagonal there. If I use, so let me make that really big. So the 4, 1, negative 5, the negative 1, 2, 1, and the 3, 0, negative 2. Let me start with the left side just for practice, nothing more. So if I take this 2 right here, that's going to end up multiplying each row by 2, and the 4 will end up multiplying both 3. So these multiply the row. And if I look at the diagonal on the right, the negative 3 is going to multiply column 1, and the 5 is going to multiply column 2, and the 2 is going to multiply column 3. Now you could multiply them by traditional multiplication if you're really stuck, but this will make life a lot easier. And that turns out to be, what is that? 8, negative 24, negative 10, and a 12, 3, negative 10, and a 0, and 60, yeah, 20 times 3, and 20, and negative 60. So multiplying on the left of a matrix, you end up multiplying the rows, and multiplying on the right, you end up multiplying the columns. Alright, now we get to the next part. Again, if you have a diagonal matrix, later on we're going to find a diagonal matrix for this purpose only. If I take a squared, well, a squared would be simply, if you have a diagonal matrix, squaring the entries, negative 6 squared, I'm going to write it out, 3 squared, and 5 squared. Alright, which is, of course, 36, 0, 0, 0, 9, 0, 0, 0, 25. Now, if I take a to the negative 2, well, you raise it to the negative 2, wouldn't that be 1 over negative 6, 1 over 36? Oh, boy. You know what I mean. This would be 1 over 9, and this would be 1 over 25. And if I wanted to take a to the negative k, that will simply be a to the negative k, 1 over negative 6 to the k, 1 over 3 to the k, and 1 over 5 to the k, and the rest are all zeros. And there it is. And that's pretty much, again, a diagonal matrix has a lot of nice properties which don't apply to any other matrix than a diagonal. And if I wanted to do the same here, it's the same deal. If I go for squaring this, well, that's simple. Squaring a negative 2, again, you negative 2 squared, that's a 4. That's a 16, that's a 9, and that's a 4. And the rest are all zeros. And if I wanted to take a to the negative 2, that's simply 1 over. So 1/4, 1/16, 1/9, and 1/4. And of course, if I want to take a to the negative k, that's simply 1 over negative 2 to the k, and 1 over negative 4 to the k, and 1 over negative 3 to the k, and 1 over 2 to the k. So in this section, we're doing a lot of inspections, a lot of kind of just applying some properties, compute the product. And do you notice that all of these are diagonals? If all of them are diagonals, then guess what? I'm going to copy the middle. Well, actually, it turns out to be fairly simple. You are going to multiply the 3 by a negative 1 times 3 times 5. And the 5 you're going to multiply by 2, 5, and a negative 2. And the 4 you're going to, the 7, you're going to multiply by a 4 and a 3. And the reason for that, if you multiply negative 1 times row 1, well, the only piece that will get it is the first. And if you multiply 5 by column 1, the only piece that will get it is the first. The rest are all zeros. And that turns out to be, let me just shrink this a bit too big. And that turns out to be what, negative 15, 0, 0, 0, 0, and 10, negative 20, and 12 times 7. 12 times 7 is 84. There. Let me just shift that up a bit. Okay, let me do some shifting. Okay, all done. Well, let's see how this works. If I have a diagonal matrix and raise it to the thousands, again, that would be simply 1 to the 1000, 0, 0, negative 1 to the 1000, and that turns out to be pretty much the identity matrix for a 2 by 2. And use what you learned in this section about multiplying. Well, if I'm going to multiply this, this is what? This is a matrix being multiplied by a diagonal on the right. If you multiply by a diagonal on the right, then you're going to really multiply the columns, if you recall, and that will be an A, B, 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 and that's pretty much it. And if you multiply on the left, so again, this is the diagonal, you end up getting a 3 by 3, the same size, that doesn't matter. You get R, S, T, U, V, W, that looks like a U, and X, Y, Z, and here, if you multiply on the left, you end up multiplying the rows. So you end up with and that would be my answer. Again, no need to actually do the actual multiplication and go from there. That's pretty much how it always works. I would like to make this a symmetric matrix. If you recall what a symmetric matrix is, a symmetric matrix is a matrix in which when you take the rows and columns, you get the same thing. So A and A transpose are literally the same thing. So if I make this a 3, basically go across the diagonal and just make sure that they match. Go across the diagonal and make sure that they match. Make that a 7, make that a negative 3, make that a 5, make that a 2, make that, that a negative 7, make that a negative 6, and there it is. Determine by inspection if the matrix is invertible. Look at the diagonals. This is invertible. And if they say why, none of the entries across the diagonal are 0. And if you look at number 22, you notice that there is a 0 there. You say this is not invertible. Why is that? Because there is a 0 across the diagonal. And last problem we have, they only want us to focus on the diagonal. So when you multiply AB, only the diagonals. So do you see that this is an upper triangular and this is an upper triangular? That is maintained. When you multiply here, you're going to get some values. They don't care what those are. What they care about is the diagonals. The diagonals, you're going to get pretty much 4 times 6, 0 times 5, and 7 times 6. So pretty much what you're getting is 2400, not 0. You're getting 0 and 42. So they're only concerned with the diagonal. They don't really care about the rest. They want to make sure that you understand these properties because we're going to use all of those later on. And that's pretty much it for this section.